We start by defining what a field is. A field is a set of elements in which a pair of operations, normally it's going to be addition and multiplication, are defined analogous to the operations in real number system. A field can be either real numbers or complex numbers. And if that field contains real numbers, we call that field a real field. And if it contains complex numbers, it is a complex field. For this module, we are going to assume that our field contains real numbers. So we're going to only deal with real field. So just to introduce a new concept called the vector space. Generally, a vector space is a space composed of objects. And in this case, those objects will be called vectors, which can either be added together or multiplied by a scalar. So a scalar will be from the field, and these objects will be inside the space. The understanding is that a vector space and the field are two separate things. But this addition, or the way you'll be adding these objects and the way you'll be multiplying these objects inside the vector space with a scalar, should properly be defined. And the way they are defined should satisfy very particular requirements. So there is this axiomatic definition of a vector space. Let V be a set on which two operations, vector addition and scalar multiplication, are defined. If the list of axioms are satisfied for every U, V, and W in V, and every scalar C and D, then V is called a vector space. So a set V, together with the definition of addition and scalar multiplication given, if it satisfies these 10 axioms, and then that set is called a vector space. So this is the definition of a vector space, which is used to prove if a set is a vector space. Knowing these 10 axioms is important in that it is what is required to show that a particular set is a vector space. However, this definition by itself is not rigorous, because what it does, it just gives us properties and characteristics of a set, which is a set which is a vector space. So we need more than this, and we need a more rigorous definition which does not use characterization and properties to tell us what a vector space is. For that, we are going to first define what an abelian group is. So if you have a set V together with a binary operation star, that set together with that operation star will be an abelian group if the following four conditions are satisfied. It must be associative, and there must be exist an identity element. Also, we must have an inverse for each element in V, and most importantly, elements in the set V must commute. Actually, the fourth property there, or the fourth condition, is what makes the group abelian, because the A, B, C just is just the definition of a group. But for a group to be abelian, you need an extra condition of commutativity. So with that definition of an abelian group, we are now ready to construct another definition of what a vector space is, which is a bit compressed and acceptably rigorous. So a vector space V over the field F is an additive abelian group, together with a map such that the following holds for scalars A, B in F and the vectors V, W in V. So instead of having 10 axioms to be satisfied, the definition of a vector space can be compressed by assuming an abelian group first, and then you just have to show that 4 conditions hold. Remember, to an abelian group has 4 conditions by itself that must be satisfied, and then we have these 4 other conditions we must satisfy, meaning that in total we have 8 conditions or 8 axioms that must be satisfied, while our axiomatic definitions requires 10. If you look carefully, if you consider this, you will notice that the 2 remaining conditions are the closure of addition and closure of scalar multiplication. The reason they are not part of this abelian version of the definition is because for us to show that the set is a vector space, first of all, we must be told how to add objects inside the set, and also we must also be told how to multiply those objects with a scalar. So the axiom of addition, closure of addition and the closure of scalar multiplication comes with the definition of addition and definition of scalar multiplication. So those two are requirements for us to show the other 8. That is why you see that an Abel version of the definition of a vector space only has 8 axioms that must be satisfied, because the other 2 comes by definition. We now have this proposition, which is fairly basic. So if you have a set V, then for every vector V in V and a scalar A from F, the following four things hold. 0 times the vector V will give you a 0 vector. A scalar times a 0 vector will give you a 0 vector. Then minus A times V will give you, it's the same as A times minus V, which is also the same as minus A times V. Remember, A is a scalar and V is a vector. Then lastly, if A times V is 0, then it's either A equals to 0 or V is a 0 vector. We have here an example. We are given a set S and the field F. We are further told that V is a set of all maps from S to F, of S into F, and we are required to show that V is a vector space over F under the following 2 operations. So they gave us the definition of addition and the definition of scalar multiplication. So to show that V is a vector space, we are going to apply the axiomatic definition of a vector space, showing that all those 10 axioms hold axiom by axiom, following the same order of axioms as we gave in the definition. We will start by closure under addition. So by the definition of addition given, For any f and g in V, f plus g is in V because that is by definition. It counts by definition that you can always add f and g and still remain in V. Next, we show commutativity. Now, if you let or consider f and g in V, so that f plus g will be equals to f plus g of x, which by definition is equals to f of x plus g of x. Now, once you have f of x plus g of x, you are now no longer inside the field. You are in the realm of f, that means the field, which means you can treat them the way you would have treated things in real case. So, and we know addition of real things is commutative. So, which means you can swap f of x plus g of x is the same as g of x plus f of x. Compressing back the definition of addition given, that will mean g plus f of x, giving us g plus f. So we have shown that f plus g is indeed equals to g plus f. To show associativity, what you are going to do, you consider three of these maps, f, g, and h in V, so that you do a less a non-strenuous algebra there, following the definition of addition given. That will comfortably lead you to show that indeed these three maps are associative. And addition identity, what is required is to show existence of a zero map, a map, in other words, a map that will not change any other map when added to it. So we do know that such a map exists and is called zero of x, which is zero, satisfying the fact that f of f plus zero equals to f, considering all the definition, considering the definition of addition we are given. Additive inverse, what you want to show is that there is a map that when you add to f, you get a zero vector, which in our case is a zero map. So such a map exists and is called for any f in V, such a map will be minus f. And following the definition of addition and applying applying a property C of proposition 1.1 we introduced, we indeed show that f plus minus f is a zero map. Then closure under scalar multiplication comes by definition, as we agreed, that is closure under scalar multiplication and closure under addition. Those are axioms which must come by definition of addition and scalar multiplication. So we are confident AF is in V just by the way scalar multiplication is defined, or just because it is defined, we are confident that the output will be in V. Then want to check if it's possible to distribute a scalar on two vectors. Now the word vector in our case is referring to a map because we are dealing with a set which contains maps inside. So what we want to show is if a multiplied by f plus g is a f plus ag. And of course, following carefully the definition of addition and scalar multiplication given, it is indeed the case that a multiplied by f plus g is equals to af plus ag. And is it now possible, or is it also possible that we distribute a vector on the sum of two scalars? Yes, when you follow the definition of scalar multiplication and addition given, you indeed show that a plus b times f is the same as a f plus bf. And As the penultimate axiom, we want to show if scalar multiplication is associative. Yes, it is indeed associative, considering the way scalar multiplication is defined. And lastly, 1 times f, is it equals to f? It, it has to, because of the way scalar multiplication is defined. You notice that all the 10 axioms are satisfied, and therefore we can conclude that V is a vector space. V is a vector space. So is the order of showing these axioms important? Yes and no. Yes, because there are some axioms which cannot be proven before other ones. No, because there is there's no emphasis on the order. So which property cannot be proven without having done the other one first? It will only affect us in these two. You cannot have you cannot show that there is an additive inverse if you have not known the addition identity. So this is the only case where order is important. You cannot you cannot show that there is an additive inverse if you don't know what the addition identity is. So that is the only thing about order which matters. Otherwise, generally, the order does not matter. It's just that you must know the addition identity first before you claim this additive inverse for each element. So that is how you show something is a vector space. And yes, thank you.